All right, today we're going to do chapter 5. But before we do that, I'd like to talk a little bit about the exam. High score was 100. Congratulations. Average was in the upper 60s. Um, you should go to Blackboard a lot, but you should go there again and check your overall grade. Now, the overall grade is not immediately visible on Blackboard, but if that grade is over 175, you're basically doing well. You have a very good chance to get an A. To find the overall grade, go to grades. Blackboard has two grades for some reason. What they call the current grade that really is not current. And it's, in this case, 10 out of 10, okay? They insist on putting this second number here. Just ignore that, please. You're looking for the first number. But to get overall grade, what you do is click on the little green shape, and that'll open. And now you can see what is the real grade. Again, ignore the second. Overall grade is what you want. Again, if you're 175 or more, you're doing well. On the exam, there was this question. Let me put some lights again. There was this question, and lots of people missed it, so I thought I would go through it very quickly. We have C3H4 with one carbon-carbon triple bond, and you want the Lewis. Okay. Carbon is here in group 4, hydrogen group 1, have 4 valence electrons, and we have 1. Okay? This is the way I do it, so it's kind of by inspection. Here are my carbons. They're the hydrogens. We have one carbon-carbon triple bond. So let's move some electrons around. Move these up as well. And now we have our triple bond. Okay? We need to place the hydrogens with these unpaired electrons. So here, 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 and here. If you count now, you'll see that this carbon has 8 electrons. So does this one, and so does this guy. Every hydrogen has 2, like it's supposed to. Make it line bond, and this is the organic compound propine. Most people didn't even get close. By the rules, first we count the valence electrons and the hydrogens. There's carbon, that's hydrogen. We have 3 carbons, 1 hydrogen, or 4 hydrogens, 16 electrons. Attach atoms to the central, so one of the carbons the middle, and give them all an octet. So these all have an octet, and the carbon doesn't. Place remaining electrons on the central atom. Well, we've used them all, so we can't do that. Next, make double or triple bonds to give this guy an octet. Well, we have a triple bond, so let's just move these guys in, and there's where we are. Finally, add hydrogens every place you have a pair of electrons sticking out. And there's propine again. Any questions? And then this one. we have 6 times 10 to the 23 moles of a gas, right?
That's a question.
How many particles is that? Well, we know our ratio here. 6 times 10 to the 23rd particles per mole. This is our given. So we start with the given, put in our ratio, moles cancel, 10 to the minus 23 and 10 to the 23, well that's 1. And 6 times 6 is 36. 36.2, but 36.
I was stuck on that for 10 minutes.
Finally, next Wednesday we're doing lab number 6. They want us to do this slightly different this time. We are doing a pre-lab online. So, go to Blackboard, week 8, lab 6 pre-lab. It's a 10-point quiz. This is the only way you earn points for this particular lab. The quiz is very simple. It's just balancing and solubility, but you must complete it before we do the lab. Now at the end of the lab, as we always do, hand in your results. But again, the points come from here. On Blackboard, week 8, pre-lab 6. Got it? All right. Chemical reactions. This is one of my favorite demonstrations to do that they won't let me do. It's thermite, it's called. Aluminum and iron 3 oxide react very violently, spit out little bits of molten iron all over everybody. It's like doing welding. It's fun, but again, they won't let me do that here. Shoot. All right, chemical reactions. 2 or more elements or compounds undergo a chemical change. They can form a compound. If characteristics of each of the substances is lost, and you get a new substance like this. In a reaction, we use an arrow to link our reactants and products. Okay? The arrow has the properties of an equal sign. That means we must have the same numbers and types of atoms on both sides of this equation. If you know, we have 2 aluminums, 2 aluminums, 6 bromines, 6 bromines. The physical state, these little letters, that it's optional, okay? But they tell you this is a solid, that's a liquid, that's a solid. AQ stands for a solution in water, aqueous. In order to make sure that we have the same numbers and types, we use coefficients. The little 2, the 3, and the 2. This gives us 2 aluminums, 2 aluminums, 6 bromines, 2 times 3, 6 bromines. The process of putting in the coefficients is called balancing an equation. In general, it's referred to as the stoichiometry of the reaction. Now, stoichiometry is a fun word. Sounds very impressive, but it's simple. You can tell people, oh yes, we did stoichiometry in class today. Just sounds good. We can express these coefficients in terms of moles. We can also express them in terms of mass. This is 2 moles of aluminum. This is 3 moles of bromine. and we get 2 moles of our product. You'll note that the sum here and here is this. So same numbers and types, and the same mass on both sides. So let's see how we come up with these coefficients. How do we balance an equation? Let's look at the decomposition of hydrogen peroxide. Hydrogen peroxide, the fizzy stuff that you put on cuts to hopefully kill bacteria. It doesn't really work, but decomposes to give oxygen gas and water. You'll note that this equation, as we have written it, is not balanced. We have 2 hydrogens, that's good, but 2 oxygens and 3 oxygens on this side. So, the way I try to approach balancing is first to try to make things either all odd on both sides or all even. We have 2 and we have 3 in terms of our oxygens. We could make it even on both sides if we simply put a 2 in front of the water. We have 2 oxygens here, 3 on this side. If we put our 2 in right here, we now have 1, 2, 3, 4 oxygens. It's even. Now, it's even, but now we have our 2, so we have 4 hydrogens. We need to get 4 hydrogens on this side, and we can do that by sticking in another 2. So we have 1, 2, 3, 4 oxygens, 1, 2, 3, 4 oxygens, 4 hydrogens on both sides, and we have balanced this equation. Now, the only way to really learn how to balance equations is by doing them. And I'll show you we have something on Blackboard that will help you. Any questions with this? Well, let's do some more. This was an exam question. I was testing whether they could write the proper formula for potassium chlorate, and of course they did. Chlorate is a parent of the chlorine family, ClO3, and they're all -1, right? Potassium is +1, so that balances out nicely. It's simply KClO3. KClO3, when you heat it up, you get oxygen gas. Now we remember that oxygen is one of the diatomic elements. So this is O2. And potassium chloride, this is -1, that's +1, simply KCl. Now, as we look at this equation, again, it's not balanced. We have 3 oxygens, we only have 2. Let's make it even first by sticking in a 2 over here. Hello? Three oxygens and only 2. Let's put our 2 out here. There we go. Okay, 2 KClO3, that's now 6 oxygens and 2 KCl's. To get 6 oxygens, we have to put a 3 in here, and 2 KCl's, just a 2. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines, 6 oxygens, 6 oxygens. We have balanced the equation. Now this is actually kind of a neat equation. a neat reaction. It's a nice, simple way to generate oxygen in the lab. Take a little tube, put potassium chloride in there, heat it with a Bunsen burner, oxygen bubbles out. It also allows you to do what's called the gummy bear reaction. This is a gummy bear. Gummy bear is essentially pure sugar. We're going to take our tube with potassium chloride in there. It will generate oxygen. The oxygen will react with the sugar. It'll form CO2 and water. Happens spontaneously. So, let's take and do this. There goes our gummy bear. That's our potassium chlorate.
Ouch!
Don't show this to small children. And yes, it consumes it very nicely, very quickly, and you're left with kind of pink potassium chloride. Any questions? All right, let's go ahead and balance some real equations. Let's see if I can do this. Okay. Our first one. We have 2 hydrogens there, 3 hydrogens here, right? Let's make them both even. I would stick a 2 in here. That gives us 6 hydrogens, 2 nitrogens. We just happen to have 2 nitrogens, that's good. To get 6 hydrogens, we need a 3 out here. I think it's right. Yes, I got it. Our next one. Let's see. We have 1 hydrogen, we have 2 hydrogens. Let's stick a 2 in here. 1 zinc, 1 zinc. This gave us 2 chlorines too, didn't it? I think we're there. Yep, that's good. Before I do it, try this last one. On the last one here, we have 3 oxygens there, 2 on this side. Let's double it, make it even. Now, when we did that, that gave us 4 irons, right? We need a 4 over here. This also gave us 6 oxygens. We only have 2, so we need a 3. Now, the chlorines, we have 4 times 3 is 12 chlorines. That's a 6. I think that works. Yep. Any questions? Let's do it again. Take these, work them quickly, and then we'll do them together. Two hydrogens, that's good. One sodium. I miscounted though. We have three hydrogens here, don't we? Gotta put a 2 in. Now we have four hydrogens. We have four hydrogens, we need two waters. We also just gave ourselves two sodiums. Oops. Is that right? Yeah. Because we have two hydrogens here and two here. So we're good. The next one. Lead plus HCl gives lead 2 or lead 2 chloride and hydrogen. Slowly, very slowly. Let's see, one lead on both sides. We have two hydrogens, we only have one. So double that. That gives us two chlorines, but that's what we've got. Like this. So, we're good, I think. And the last one. Here we're dealing with a polyatomic ion, nitrate. Oops, wrong button. Here we're dealing with a polyatomic ion. When you're dealing with polyatomics, just treat it as a lump. Don't do a nitrogen and three oxygens, whatever, just a lump. So we have one nitrate here, we have two over there. Let's double that. That gave us two silvers. So that's good. One magnesium on both sides, two chlorines, two chlorines. Yep, that one worked. Now, of course, there's a tutorial here. Balancing chemical reactions, it's called. On the one online, there will be little fields here. You simply enter the number. If there's only one of something, you have to put a 1 in. Same thing on Blackboard, a 1, and put in your numbers. Okay. This is the organic compound ethene reacting with oxygen to give CO2 and water. Right away we see we have two carbons, only one. So let's put a 2 in here. We have 1, 2, 3, 4 hydrogen, only 2 here. And the oxygen, 1, 2, 3, 4, we need a 2 in, a 3 in there, that's right. It's 4, 6 oxygens. I think that's right. Oh, I forgot my 1. Blackboard will not be as forgiving as I am. If you don't put the 1 in, it doesn't work. Any questions?
Why must we enter the number 1?
I'm sorry?
Why must we enter the number 1?
Well, you have to if there's only one of something, 1 mole involved in the reaction. The reason that you have to do it on Blackboard is that Blackboard cannot evaluate an empty field. It has to have a number. So, all right, calcium carbide reacts with water. Really neat reaction. It gives acetylene gas and calcium hydroxide. Now, this is a very useful reaction. Acetylene gas is what they use in welding torches and stuff like that. And this reaction actually used to take place on the helmet of miners. Before they had electric lights down in the mines, there would be a little thing of calcium carbide here. You push a button, go into some water in the bottom, and you would light your head on fire. And that's how you saw. Okay. All right, let's balance this equation. 2 carbons, 2 carbons, that's good. 2 hydrogens, 2, 4 hydrogens. Gotta double this guy. 1 calcium, and I guess that's it. Now on blackboard, once again, you have to put a 1 in here, and a 1 in there, and a 1 here. Okay? For me, calcium carbide has a slightly different memory. When I was a child in the 50s, they had something called a bank site cannon. The bank site cannon, you would put calcium carbide in here, put water in the bottom, do this, some would dribble in, make acetylene, and then you would push the button, make a spark, and away it would go. Something like this. Really neat. You could stuff all sorts of stuff in here, and it would shoot it all the way across the yard. They don't sell them anymore. It's a shame. Okay. Here's the thing that's on Blackboard, equation balancing worksheet. No credit for this. This is just for practice. And there's a bunch. There's also an answer sheet so you can check it as you go. Again, the more you balance, the better you get at it. Okay. Next, we're going to talk about reactions. And we're going to do types first. Now this is a lot like biology, I suppose, where we just put names on things. But we'll see that naming types of reactions is important if you want to go back and try to predict what the products will be for a given reaction. Synthesis and decomposition. In synthesis, we make a new substance. Decomposition, we take something and break it down. Pretty simple, pretty obvious. For example, carbon plus oxygen gives CO2. Think of barbecue. It gets hot. When you have a chemical change happen, quite often it's very obvious. This is very hot. It burns. Sometimes you'll get gas evolved, whatever. This is synthesis from the elements. We can also do synthesis reactions with compounds. Again, this is ethene, HBr, bromoethane. Simple organic reaction, but again, compounds and elements all work. Decomposition is simply synthesis backwards. Copper 1 sulfide, if you warm it up, gives copper and sulfur. Decomposition into the elements. You can do it with compounds as well. Calcium carbonate, if you heat it up, you can get calcium oxide and CO2. Now, this is a neat reaction. The Romans were among the first to actually exploit this, because if you take calcium oxide and you add water to it, make a slurry, the reaction will reverse and you'll make calcium carbonate. Now, what is calcium carbonate? Marble, limestone, chalk too, but this is how the Romans made the first concretes. Kind of neat. Displacement reactions. We will have both single and double replacement reactions. In replacements, two compounds, element and a compound, react so that they are switched. Okay? This is a single replacement reaction. We have an element and a compound reacting to give an element and a compound. But what we've done is swap the fluorine for the chlorine. In general, the rule is that when you have a single replacement, metals will replace metals, non-metals will replace non-metals. The signature for a single replacement, element and a compound, giving an element and a compound. A double replacement. Oh, we did this, that's right. We did this in lab, didn't we? We took our nail, stuck it in copper nitrate solution. What happened was we had copper form on the surface of the nail. And at the same time, we made iron to nitrate. Element and a compound, element and a compound. This is a double replacement reaction. In a double replacement, ions simply swap. So, the chloride, in this case, will pair with the silver, and when it does, it forms silver chloride, which is insoluble in water. It's a solid. In order for a double replacement to run at all, you have to either form a precipitate, that's a solid, or evolve a gas. The nitrate pairs with the sodium, and we get sodium nitrate. Redox reactions, oxidation and reduction, called redox. One or more atoms will undergo a change in oxidation state. Now, we talked about oxidation states, oxidation numbers, back in chapter 3. Today, we're going to do it right, do all the things, but it's not that difficult. Back in chapter 3, we said that elements, by definition, had an oxidation number of 0. We also said in chapter 3 that oxygen was going to almost always be -2. Now, in order to make this a neutral compound, since we have 2 of them, that means that the carbon must be +4. This is a redox reaction because the oxidation number of carbon has changed from 0 to +4, oxygen 0 to -2. It's also a synthesis reaction, so there's a lot of overlap. Any questions? Well, look at these guys. Tell me, are they synthesis, decomp, or replacements? Our first one, pretty obvious. We have hydrogen reacting with nitrogen to give ammonia. We're making something, aren't we? Something new is synthesis from the element. Here we have lead 4 chloride reacting with fluorine to give lead 4 fluoride and chlorine. Element, compound, single replacement. Here we have sodium sulfate reacting with barium chloride. We get solid barium sulfate, that's a precipitate, and sodium chloride. This is a double replacement reaction. We're just swapping ions, and making a solid. Any questions? Let's do another set. Hydrogen peroxide, oxygen, and water. We just did this one. It's a decomposition, isn't it? We're starting with one substance, making two new ones. Now, most people look at this and they say it's a replacement, single replacement, but it's not, is it? We have an element and a compound, but just a compound here. This is just a synthesis. We're putting those two together to make PCO5. And finally, element and a compound, element and a compound, the signature of a single replacement. All right, so those are our basic reaction types, okay? I said that the point in trying to classify reactions was so we could better predict products. If you're doing a synthesis reaction and you're involving things with metals in it, what you do to predict is to utilize the common charges for the elements. Put them together and give it your best guess. Now, anytime you're doing predicting, you're guessing, but you can usually do it pretty well. We've seen this before. This is a solid aluminum reacting with bromine. Again, there's evidence for a chemical reaction. It gets really hot, starts to burn, whatever. On Wednesday, when you do these things, look for things like precipitates, look for things to get hot, whatever. All right, what do you suppose is happening? Well, we're going to make an ionic compound because we have a metal. The metal aluminum is typically a +3. Bromine, a halogen, will be a -1. Our very best guess here is 1 aluminum and 3 bromines. Any questions? Well, I hope you've noticed the equation is out of balance. Very quickly balance it. We have 2 bromines, we have 3. Let's double this. That gives us 2 aluminums. We need another one over here. And we need 3 Br2s. I think that works. If we're doing a synthesis reaction that doesn't involve a metal, so it's non-metal elements, what you do is the valence electron deal. We've seen this one before as well. Hydrogen reacting with oxygen to give something. Let's just watch it again because it's fun. Balloon has hydrogen, room has oxygen, and it goes boom. All right. You look at this and you say it's going to be a molecular compound. So we look for valence electrons. Hydrogen has 1, oxygen, group 6, has 6. So here's our 2 hydrogens. We need an oxygen, group 6 with 6 electrons. It just fits nicely in there. Make our bonds. And yes, we just made water. Any questions? Except it's not balanced, is it? 2 hydrogens, 2 hydrogens, 2 oxygens, 1 oxygen. Let's double this. That gives us 4 hydrogens. We need to double that as well. And this is the neatest reaction you'll ever see. It's the neatest little video. For decomposition, nitrogen triiodide. Extremely easy to make, okay? You take ammonia dissolved in water, you add iodine, and this black stuff just kind of comes out of solution. You take it and you filter it. So these are just little smudges of nitrogen triiodide on filter paper. And let them dry. Once it's dry, this is perhaps the most sensitive contact explosive that we know of. We are going to touch one of these with a feather. Okay? Yep, it's a feather. And do it again in slow motion. Very, very sensitive stuff. Got to be careful unless it's wet. Okay, what in the world is going on? The clue comes from this purple haze. Turns out that iodine is purple and has a high vapor pressure. This is most likely iodine. I think we are decomposing into the elements. That would give us iodine and nitrogen as products. Things that explode quite often will evolve nitrogen. That's another giveaway. We are not balanced, of course. We have 3 iodines. We only have 2 here. That gives us 2 nitrogens. That works. And that's needed free to balance that out. Any questions? All right, predicting single replacements. That's pretty simple. We're going to take an element in a compound and make an element in a compound. We remember metals replace metals, non-metals replace non-metals. So, again, we have our lead for chloride and fluorine. These will react. We will get the non-metal replacing the non-metal. And get lead for fluoride and chlorine. Simple as it can be. Charges don't change. Lead 4, element, element. It's not balanced. We have 4 chlorines, we only have 2. We have 4 fluorines, we only have 2. Now we have 4. There, now that's right. 1 lead, 4 fluorines, 4 fluorines, 4 fluorines, and 4 fluorines. There are 2 notable exceptions to our metal, non-metal rule. And these are perhaps the most important industrial reactions that involve single replacements at all. The first one, if you take copper 1 oxide, expose it to hydrogen gas, you get copper. We have an element and a compound, we're getting an element and a compound, but hydrogen is pretending it's a metal. It's not. But it can pretend, can't it? This is how you make copper. Iron 3 oxide with carbon. Element, compound, element, compound. But again, carbon is winding up in a compound, and carbon is pretending again to be a metal. Why is this so important? We're making iron. This is what they do in dairy. Iron 3 oxide and carbon. Double replacements. Again, all we're going to do is swap ions. One more time though. In order for a reaction to go, you must form a precipitate, that's a solid, or evolve a gas. Here we have potassium sulfate reacting with barium nitrate. If it's a double replacement, we will swap the sulfate, it'll go to the barium, the nitrate will go to the potassium, and that's what we will get. Turns out that barium sulfate is a solid, so this reaction proceeds as it's written. One of the hallmarks of general chemistry is stuff like this. This is potassium iodide, lead nitrate. We will get solid lead iodide out of this, and potassium nitrate will stay in solution. You'll see both of these are nice clear liquids. We take a nice squirt of one of them, squirt it in the other. Instantly you see the formation of solid lead iodide. In lab, you would take this, put it in a centrifuge, spin it down, get a little lump of lead 2 iodide at the bottom. Any questions? Well, one of the questions you should have is, how in the world did I know that lead 2 iodide was a solid, or barium sulfate, or silver chloride? Because I know the rules. Solubility trends. First one is really simple. If your cation, if the metal is from group 1, regardless what you pair it with, it'll be soluble. That and ammonium as well. They're all soluble. That's good, that's simple, easy to remember. Nitrates and acetates are also all soluble. Good, nitrate acetate, group 1. Then it gets a little messy. Almost all metal halides, group 7, are soluble, except for these guys we refer to as the heavy metals, silver, lead, mercury, and copper. Those are insoluble. Metal sulfate, same thing, except there's a different group. Barium, lead, and calcium are insoluble. With the exception of these guys, metal hydroxides, oxides, and sulfides are insoluble. So if it's not a group 1 or ammonium, and it's one of those, it's insoluble. And finally, same thing for carbonates and phosphates, they're insoluble in water. Now, let me be technically correct here. When we say something is insoluble, that's wrong. It is very, very, very slightly soluble. But, I mean, the tabletop is slightly soluble, okay? But, for all intents and purposes, it's insoluble. Let's look at a list. Silver nitrate. We remember silver is a bad guy, but that's what chlorine is. Silver chloride. But this is a nitrate. Anything that's a nitrate is soluble. Magnesium chloride. The rule says that most metal halides are soluble, except for a few that aren't. Magnesium is not one of the bad guys, fully soluble. Silver, lead, mercury, and copper are not. Most sulfates are soluble. Plus, this is group 1. It's a soluble. The ones that are not, once again, barium, lead, and calcium. Silver chloride, well, there she is. Silver is our heavy metal. The metal halides are mostly soluble, except for those guys, insoluble. Barium nitrate. Well, it's a nitrate. All nitrates and acetates are soluble. Lead 2 iodide, we just saw that. It's a lovely shade of yellow. Most metal halides are soluble. Lead is one of those that is not. Lead, silver, mercury, copper are not. Magnesium nitrate, again, it's a nitrate. Of course it's soluble. Most metal sulfates are soluble. The ones that aren't, well, barium is the big player here. Barium sulfate, insoluble. Metal halides are soluble. Iron is not one of the heavy metals. It is soluble. And finally, what is this? That's acetate, right. Just like nitrates, all acetates are soluble. Sometimes you will see it written like this. This is the way an organic chemist would write it. In general chemistry, they write stupid, something like this. Doesn't tell you what it is at all. This does. Any questions? All right, now we know all about solubility. If we take silver nitrate, react it with potassium carbonate, what do we get? What's the rule for carbonates? They're all going to be insoluble, aren't they? We're going to swap here, get silver carbonate, potassium nitrate. Is that balanced? Certainly not. We have 2 silvers, we have 1 silver. Let's see, that gives us 2 nitrates. We only have 1 nitrate. Now I think we're good. Copper nitrate, potassium carbonate. Carbonate will pair with the copper and form a precipitate. Now, are we balanced? Nope. We have 2 potassiums, we have 1. We have 1 copper, 2 nitrates, 2 nitrates. I think we're good. And finally, aluminum will pair with the carbonate to give insoluble aluminum carbonate. We have 1 aluminum, 2 aluminums, we need another. Let's see, one carbonate, oops, two carbonates. Oh, six nitrates, right, all those nitrates. And finally, three carbonates, yes, that's what we need. Any questions? Well, then let me relax for a second. Look at this assortment. Predict the one that's insoluble, and then balance the equation. In our first one, we're going to make silver chloride. That will be insoluble. And we will be left with magnesium nitrate. Now that's not balanced. One silver, two chlorines, one chlorine. Oops, we have to put a 2 in. That gives us two silvers over here. The magnesium is fine. Do the next one. Barium will pair with the sulfate, or barium sulfate, very insoluble. Sodium nitrate is left. We have two nitrates, only one. Two sodiums, only one. One barium, one sulfate. I think if we just double that, we'd be good. Lead nitrate is soluble. So is sodium sulfide because it's group 1. Lead sulfide, however, is not. Remember, oxides, sulfides, hydroxides, all those things are not. So we will get lead sulfide as our solid. We'll also get sodium nitrate. Now here we have two nitrates, only one. We have two sodiums, that's good. I think all we have to do is double up the sodium nitrate.
Does it matter in the products? Does it matter which one you put first?
Nope.
I could put NaO3 plus PBS.
Yeah.
Okay.
Yep. I was going to say something. Oh. You'll note that as we do these things, you will see the same solids over and over again. Okay? There are a few that you just really have to know. Silver chloride's a big one, barium sulfate's a big one. Lead sulfide, lead halides, all of those are big guys. Okay? Some of the other ones are not quite as important or common. So just focus on the ones we talk about. All right, now comes the big part. We're doing oxidation and reduction. These reactions involve the electron donor and an electron acceptor. We will transfer electrons, okay? As we transfer electrons, the oxidation numbers will change. If the oxidation number increases, we refer to that as oxidation. If it decreases, that's reduction. Well, that would make sense, I suppose. I always have trouble with this, with these definitions, and it gets worse. But what I always remember is that in order to get an increase in oxidation number, something has to lose electrons. So just remember, oxidation, loss of electrons, and the other one's reduction. Oxidation, loss of electrons. All right, what is an oxidation number? Again, back in chapter 3, we said it refers to the ground state of an atom. All elements are zero by definition. If you're dealing with an ionic compound, same thing with a metal, the oxidation number is the same as the charge. Magnesium bromide, magnesium is +2, bromine is -1. Oxidation terms, +2, -1. Here we have lithium phosphide, +1, -3. Oxidation numbers are the same, +1, -3. So if it's got a metal in it, you're set. Just do the charge on both species. Here are the rules. Elements are zero. Group 1 are +1. Group 2 are +2. So these guys make it simple. Fluorine, most electronegative element, is -1. Always. Now it gets a little more interesting. For hydrogen, you can make a metal hydride. In that, the hydrogen will be -1. Otherwise, it's +1. If it's bonded to a non-metal, it's +1. A metal, it's -1. Oxygen will be -2. Halogens will be -1. So for selenium, they want to be just like oxygen, and they're -2. Let's see how we do this. This was an exam question in one day, but 1 point. We have SO3. It's a molecular compound, isn't it? So no metals, not the easy one. But it has an oxygen, it has 3 of them. We remember oxygen is always going to be -2. Now the compound itself has to be neutral. So this is 6 negatives. That means the sulfur must be a +6. That's not hard. Nitric acid, HNO3. We take nitrate, that's NO3, put a hydrogen on one of the oxygens. Now, in this compound, the oxygens will be -2, and because the hydrogen is bonded to a non-metal, it will be a +1. Now, to make this neutral, the nitrogen in the middle, we have 6 negatives, 1 positive. This nitrogen must be +5. Any questions? On your exam, number 2, you will probably have a question something like this. There's a tutorial, oxidation numbers. This one, what's the oxidation number of lead in lead nitrate? Well, you say to yourself, that's easy. Lead's a metal. What's the charge here? Well, nitrates are 1 each, minus 1. So this must be a plus 2. And that's it. Now this next one is a little strange. pH 3. We're looking for the oxidation number of hydrogen. Well, both of these are nonmetals, aren't they? Hydrogen bonded to a nonmetal is plus 1. That makes the phosphorus here a 3. Minus 3. Any questions? All right, how do we recognize a redox reaction? Again, oxidation, loss of electrons. Remember that. Reduction is gain of electrons, but you only have to remember one of them. Let's look at a simple reaction here. We have aluminum metal reacting with iron trioxide to give metallic iron and aluminum oxide. An element and a compound, element and a compound, single replacement, right? Right. Is it redox? Well, the aluminum and iron are both elements. So this is going to be 0. Iron is going to be plus 3. Oxygen will be minus 2. Okay. Over here, iron is an element, so it's 0. Aluminum will be plus 3 because it's an ion. Oxygen will be minus 2 as well. So, is this redox? Well, I think so. Aluminum has changed from 0 to plus 3. Iron from plus 3 to 0. So yes, it is a redox reaction. Now, which elements or compounds, whatever, have been oxidized and which have been reduced? Remember, oxidation, loss of electrons. Aluminum went from 0 to plus 3. To do that, it had to do what? Lose 3 electrons, right? Iron went from plus 3 to 0. It had to gain 3 electrons. Aluminum has been oxidized. Iron has been reduced. Now, just to make this confusing, there's another type of terminology that is in common usage. Iron is oxidized, right? How did it get that way? It's because the iron here is an oxidizing agent. Likewise, the aluminum reduced the iron here, so it's a reducing agent. It's oxidized, makes it a reducing agent. It's reduced, makes it an oxidizing agent. You don't have to know this, but general chemistry, they would love to do this because it makes it so confusing. Okay, I won't be confusing. Now this reaction, we saw it earlier. This is the thermite reaction. single replacement. Here we have a flower pot. Flower pot is full of aluminum and iron trioxide, just mixed up, both solids. Flower pots have a little hole at the bottom, right, for water. So there's a hole in the bottom of the top of it. This one is a big pot and it's full of sand. We are going to come with a piece of bodium magnesium ribbon, stuff it in the top. Just watch. And watch. Now as it's going, pay attention to what's happening at the bottom here. And it's still draining out. You can see there's a dribble coming out here. That's molten iron. Some of the dishes you've never done this done. But when it is finally done, down here in the sand, that's white hot iron. That kind of neat. Once it cools, you can tell it's iron. It's a nice little dark lump. I did one of these thermites in a big classroom with 500 people, and did it up on the lecture thing. People in the front row got splattered with molten metal. Yeah, a little, like welding. But it kept relighting. So I thought it was done, and I started lecturing again, and it took off again. So, yeah, you gotta be careful. This is a fun reaction. Unfortunately, with things that are fun, people find bad use for them. This is a thermite bomb. It's an incendiary device. It's dropped on people's homes. This is from World War II in England, the victim of a thermite bomb attack. Nasty stuff. What a fun reaction. All right, let's just determine if these are redox or not, and pick out who is oxidized and who is reduced. In our first one here, we have tantalum reacting with bromine to give tantalum bromide. Both of these are elements. They're zero. Bromine is a halogen, it's -1, making the tantalum a +5. Who has been oxidized, who has been reduced. Let's just do oxidized. Who was oxidized here? Tantalum went from 0 to +5. To do that, it had to lose 5 electrons, right? That makes the bromine reduced. Aluminum oxide plus silicon. Silicon dioxide plus aluminum. We're going to be 0 for the silicon, +3 minus 2. Silicon has gone from 0 to +4. Aluminum from +3 to 0. Who was oxidized? Silicon is oxidized, aluminum reduced. Sodium sulfide reacts with lead nitrate to get lead sulfide, that's insoluble, right? And sodium nitrate. Is this redox? Well, there are no elements. Sodium will be +1 minus 2. Lead is its charge, that's +2. Nitrate's -1. The nitrate is made up of a +5 and 3 O2 minuses. So, who has been oxidized? +1, +1. -2, -2. +2, still +2. And that's nitrate. Nobody's been oxidized, have they? This is not a redox reaction. Double replacements are never redox. Just so you know.
I'm confused with where you get the numbers from. Like the +1, -2, like how you get the
These are
numbers?
metals, so it's just the charge. Sulfur wants to be just like oxygen, so it's a -2. It's all in the rules.
Okay,
Element, compound, element, compound. Single replacement. Nickel will be +2. Hydrogen 0. Nickel is 0. Hydrogen +1. Chloride -1. Nickel has gone from +2 to 0. Hydrogen from 0 to +1. There is a change. Who was oxidized? Hydrogen started at 0, lost an electron. Hydrogen is oxidized, nickel reduced. Any questions? All right. If you do the tutorial and something like this comes up, just click on new problem and try it again, because this is a difficult one, that's why I'm doing it. Because it's confusing. Here we have a redox reaction. This is called a half reaction. In a half reaction, you only put in the reactant species and ignore everything else, because they just stay the same, right? So here we have antimony oxide and vanadium oxide reacting. We're only concerned with the vanadium, so just with this guy and this guy. VO +2 and VO2 +1. So let's work on this guy first. The oxygen will be a -2, right? But this little polyatomic ion has a +2 charge. That means that the vanadium is providing the extra pluses. 2 of them to neutralize this, and 2 for this guy. VO has a +2 charge, oxygen is -2, vanadium must be +4. +4, -2, 2 left over. VO2 with a plus charge. Oxygens will give us 4 negatives. The vanadium must neutralize those and have 1 left over. Vanadium must be +5. Okay. With regard to the vanadium, we started at +4, we're now at +5. Did it gain an electron or lose one? It lost one, it has been oxidized. I don't think I put this one on whiteboard. This is another half reaction. thorium, plus 4 to thorium, the element. Thorium here is plus 4, here is 0. To get from plus 4 to 0, what do you have to do? Gain 4 electrons. It's a reduction. Any questions? It's one of the more difficult tutorials. Okay, let's do our last topic for the lecture, and that's the activity series. This is the activity series. It's a bunch of metal ions, and it's arranged according to reactivity. These guys react with water right away. These react with acids, and these are very unreactive. Hydrogen fits in the table right here. In this half reaction, we have sodium reacting with hydrogen, H plus, to give sodium plus H2 gas. That's one of the reactions with water. Sodium is here, hydrogen is here. The higher it is, the more reactive it is. There's a general rule, because we're dealing here with an element and an ion. If the element is more active, so that's higher up than the ion, the reaction will occur as written. So this is up, it's the element, this reaction goes, and it's very reactive. Look at another one. Silver is our ion, copper is our metal. Now they're both down here, but copper is above silver, isn't it? That's our element. The element is above the ion. This reaction will occur as written. This is a standard reaction. We used to do this in Lab 6, but they changed it, changed everything. But it's a cute reaction. We're going to take a copper wire and stick it into a silver nitrate solution here. So it's a nice, bright, shiny copper, right? As it sits in there, after just a minute or so, it starts to turn fuzzy. That's silver metal being deposited on the copper, just like the iron, nail, and copper solution. After 8 minutes, and after 20 minutes or so, you can see the solution is turning blue from the copper ion, and we have lots and lots of sodium. Why is it blue? Again, copper nitrate is a blue substance. Silver nitrate is also expensive, so I have a feeling that they did away with this part of the experiment because, well, it's expensive. Copper, iron, and our iron nail. Reaction went just like it was supposed to. Now here's a test question. Here's a series. Aluminum plus lead-2 or lead plus aluminum. Which one goes and which one doesn't? What's the rule? If the element is above the ion, it works. Element, ion, this one doesn't do it. All right, let's wind up all of this with 2 or 3 more questions. Aluminum and chlorine react to form a compound. What do you think it is? And which statement is correct? Well, aluminum and chlorine. We've seen aluminum and bromine react, haven't we? They form aluminum bromide. This is most likely aluminum chloride. So, compound will be ionic. Of course it will. It's got a metal. Oxidation number of aluminum in the reactants is 0. Is the reactant? It's an element. It's a 0. Molecular formula is AlCO3, most likely. All those are correct. Which are going to be insoluble or very, very slightly soluble in water. Barium sulfate was one of the big ones, right? So was lead iodide. This is a nitrate. Of course not. Of course it's soluble. A and B. All right. The oxidation number of fluorine does what? Changes from 0 to -4. Well, it is 0 here, but it's -1 here. Does not change. Well, yes, it does. Goes from 0 to -1. Is -1 in the reactants? Nope, it's 0 in the reactants. None of these are correct. Ox numbers for N2O5. Simple. Oxygen will be -2, right? We have 10 negatives. Nitrogen must be +5. And finally, let's do chlorous acid. Again, chlorous acid looks like this. This is chlorate with one of the oxygens having a proton. It's a nonmetal, so this will be a +1. Oxygen will be -2. So we have 6 negatives, 1 positive. The chlorine in the middle must be +5. Okay, that's the chapter. Couple things. If you came in late, Wednesday's Lab 6 grading is through the Lab 6 pre-lab on Blackboard. You must do that before you come to lab. Otherwise, you'll just go nuts with the balancing and stuff like that. And again, you do hand-in results to get full credit. Okay. There's pre-lab 6 in week 8. Any questions?
Are you going to open the new tutorial?
It's open. I believe so. I will double check. We have 3 tutorials from today: balancing, ox numbers, and redox. You want to do those. Now, many of you did lots of tutorials, and that was good. That really helps your grade, doesn't it? That's good. It really helps. But here's a real incentive, okay? Here's a real incentive. After you take exam 2, if you have 350 total points, that's in your overall score, I will give you an A on the spot, and you will not have to take the final exam That's worth saying again. And oh my goodness. After completing exam 2, if you have 350 as overall points, you get an A and no final. Once again, I said, oh my goodness. And once again. Here's our tutorials from today. Do them. I will double check right now to make sure tutorials 2 is open. All right, guys. Have a good day. See you on Wednesday. Do not forget to do the pre-lab. If you came in latish, your exam is probably up here.